Hello everyone and welcome to Tutor Terrific. Today we are going to prove or derive the law of cosines. And here is one example of the law of cosines that most people are familiar with. We have here a squared equals b squared plus c squared minus 2bc cosine a. And now you see why it might be called the law of cosines. The law of cosines is used to solve oblique triangles. Now, oblique triangles are triangles that do not have a right angle. All triangles that do not have a right angle are grouped together and called oblique triangles. Now, oblique triangles are named the following way: sides A, B, and C. And then each side has an opposite angle, which is denoted by the same letter, but capitalized. So here we have side A, and opposite that we have angle A. Now, if you're also familiar with the law of cosines, you know that there are 5 different forms than this that the law of cosines can be written in. Now, I'm going to derive this form and show you how it leads directly to the other 5. Now, if you saw my law of sines video, you know that I used an acute triangle as my illustration for the derivation. I'm going to do the same thing with a very similar acute triangle for the law of cosines derivation. However, I'm going to place this triangle in a certain way in the Cartesian coordinate plane, such that angle A is at the origin. Now, it's important for this particular derivation that I label angles B and C, their vertex locations, with coordinates. And so angle B, you notice that it is a length C, side C, away from angle A. Its coordinates on the x-axis will be C, 0. In addition, another important point is the vertex of angle C. I'm going to label this as a distance x in the x direction and a distance y upwards in the y direction away from the origin A. So its coordinates will be x, y. And now I'm going to set up 2 trig functions of the origin, angle A. Notice how, with the altitude y, I've created 2 right triangles. We are going to use those. First, I'm going to denote what the cosine of A is. This is the law of cosines after all. Cosine of angle A will be adjacent over hypotenuse. So x over b. Remember, x is this partial distance along the bottom side, C. So cosine of A equals x over b. And I'm going to label what the sine of A is. Let's look at the sine of A. It will be opposite over hypotenuse. So the altitude y over b. Okay. Now what I'm going to do is I'm going to solve both of these equations for x or y, whichever one the equation has. And so here I'm going to have to multiply both sides by b, and here I'm going to have to multiply both sides by b also. And so what I have is that x equals b cosine A, and y equals b sine A. Okay, the next step is to write a particular distance formula, and that will be for side A. Now, the distance formula, if you are not familiar, is basically a use of the Pythagorean theorem between any 2 points on a Cartesian coordinate plane. In general, the distance formula between 2 points is the second point's x-coordinate minus the first point's x-coordinate squared, plus the second point's y-coordinate minus the first point's y-coordinate squared. Now we're going to apply that to our particular situation to find the distance of side A. So the distance of side A will be the square root of, we will choose the point C as our second point and point B as our first. So x2 will just be x minus x1, which will be c squared in our particular situation. And then we will add to that the second y value, which is just y, minus the first y value, which is 0 squared. We will square both sides to get rid of the radical, or the square root, and we will have a squared equals x minus c squared plus, now I don't need to write the 0 again. I can just write y squared. Okay, now we've done a big part of the derivation already. What we will do now is we will take our expressions for x and for y and we will substitute those in at this step. So here at this x we will write b cosine a, and here at this y we will write b sine a. So a squared equals b cosine a, that's the substitution for x, minus c squared. And then y will be replaced with b sine a squared. Okay? And now we will have to expand this first term here because it's a binomial. One term, two terms. So we're going to have to FOIL that. So I'm going to move up here. I'm going to get this all in one slide. So I'm not going to write very big here. So if we FOIL this, we will have the first term squared. So a squared equals b squared cosine squared a. Then, as you know from FOILing, that the middle two terms, the cross terms, can actually be combined such that you have the product of the two terms doubled. So we'll have negative 2cb cosine a. That might look familiar to you. And then we subtract c squared. Now in addition to that, I also have b sine a squared. So those four terms are going to be simplified now. What I'm going to do is I'm going to erase all this and just write that one term, that one step, so that we can use the rest of the page to finish. Okay, I have written it up here. The only difference you'll see from when it was down here is that I have reordered the terms here that are being multiplied, and you're allowed to do that because of the commutative property. b times c is equal to the original c times b. All right, you'll see why they did that in a second. It's a minor detail. What we're going to do now is I see that there are two terms, the first and the last of all four, that have a b squared. I'm going to combine those at the front. A squared equals b squared. Now I'm factoring that out, so in those two terms I have left cosine squared a plus sine squared a. In addition, I have made a slight error here. When I FOILed the negative c, I should have positive c squared. So make sure when you FOIL a negative at the end, if it's the last term, you're doubling by, in other words, you're multiplying a negative by itself, so it should be positive. So I'm going to close this parenthesis and I'm going to write the remaining terms. Okay, I'm going to put the c squared first. I'm going to put this term last. Again, commutative property, I can reorder these. I think you can see what's taking shape. Now, this part is ugly and cumbersome, but guess what? It is a Pythagorean identity. Cosine squared of an angle plus the sine squared of an angle equals 1. Now, if you look on my channel, you're going to find the proof of all the Pythagorean identities using right triangles. But this is, in fact, true. So now that this equals 1, this is a lot smaller. A squared will equal b squared times 1 plus c squared minus 2bc cosine a. Voila! We have the law of cosines that we are most familiar with. And we are finished. Excellent. Now, there are 5 other versions of this. Namely, b squared equals a squared plus c squared minus 2ac cosine angle b. And c squared equals a squared plus b squared minus 2ab cosine angle c. Now, how are these derived? Well, all you have to do is reorder your labels. So for instance, if I wanted to solve for and derive the middle one, I would relabel my sides like this. I would put angle A here, I would put angle B here. I would keep angle C at the top, and I would reorder these two sides as well, so that each angle and opposite sides have the same letter. All these changes leads to this particular law of cosines formula, and you can reorder them in a different way to get the third one. And the last three are a group as well, which have a cosine of an angle by themselves. Well, very easily they are derived from these three equations, solving for the angles themselves. For example, the formula for cosine of A equals a squared minus b squared minus c squared over negative 2bc. All I've done is subtract the b squared and the c squared to the other side and then divided by negative 2bc. The other two are derived in a similar fashion. Let's solve for cosine b using the second formula on the left. Cosine b will equal b squared minus a squared minus c squared over negative 2ac. Again, solving for cosine b the same way I solved for cosine a. And lastly, I can get cosine c using this last formula here. Solving the exact same way, I will get c squared minus a squared minus b squared over negative 2ab. So, finally, we have the law of cosines in the 6 ways it is often shown. And I know that's a lot more complicated than the law of sines if you watch that video, but it is just as useful for solving oblique triangles. So, thanks for watching, and this is Falconator signing out.